because the speech data required a special kind of treatment. So this exercise, lab 9, don't look at this lab 9 exercise, which is a part of your Siamese. So you just take this as a generalized data preparation task for speech data or even music data or anything you deal with audio files, music, audio, or speech related files. Because what is the frequency range of audible sound range? You know that 20 hertz to 20 kilohertz. Okay, and speech data set, 300 hertz to 3300 hertz. So obviously speech is a subset of the audible range, right? So here we are dealing with the speech record. So you need to have some fundamental knowledge about the speech frequency range and all, which is going to be helpful for your understanding related to the Fourier spectrum and short-term Fourier spectrum, respectively. So most of the human speech frequency range follows this range. So I could say that nearly 80%, 80 to 90% of the frequency content will fall in this range. Then you may ask, what about the remaining? So the remaining are 10% or even 20% that will vary to male or female speaker. So something above 4 kilohertz to 5 kilohertz, this range, okay. This is the comparatively high frequency range for the speech. Because as I told you, maximum you could see the traces 3.3 or worst case 3.5 kilohertz. Beyond 3.5 kilohertz, generally for the male speakers, hardly we notice any traces beyond the 3.5 or even 4 kilohertz and all, very, very negligible. So for male speakers, you could see around 5% to 8%. So that means nearly 90 to 95% occupies in this frequency zone. Okay. So you can consider this portion is relatively low frequency compared to 4 kilohertz to 5 kilohertz, isn't it? So, but on the other hand, the frequency of the female speakers, it occupies more percentage of the frequency component beyond 4 kilohertz. So I can say even up to 20 to 25%. So this portion, it occupies around 80%, 80 or 85. The remaining. So there is this, even if you analyze the high frequency portion, you can easily discriminate male or female speaker. But here the concern is, okay, here the concern is much beyond the discrimination, much beyond the discrimination. That means what? Matching. If the same male speaker, I'm comparing with another male speaker, it's not just about the discrimination. Whether this male speaker, okay, it's male speaker, let us assume this is a male speaker anchor, male speaker positive, or what is the matching goes on between the male speaker anchor versus male speaker negative. So in the previous session, I have played the 3 audio waveform to you, isn't it? Record 1, record 2, and record 4. Okay, consider record 1 is anchor. Okay, record 1 you consider as an anchor. Record 2 you consider as a positive because it's my own voice, but little bit I modulate while speaking. Okay, of the same sentence. And obviously, record 4, whatever I shared with you, is negative. Okay. So physically, if you look at the plot, it looks same in the time domain. Obviously, it's very difficult to notice any difference. So that is why we are going to explore that in the frequency range. So one side you look at this, okay, as an extended application of the CMS for one-dimensional data. On the other hand, you learn this technique as a generalized approach for any sequence data modeling. In the foundation course, we have studied encoder-decoder architecture using LSTM architecture. Okay, we are going to extend that idea here also in the form of encoder-decoder architecture. But instead of using LSTM, we are going to use a transformer architecture. So the transformer architecture, it's going to utilize some three key components. Okay, after wrapping up this exercise, maybe from 8:15 onwards, I'm going to talk about that. I'm going to give the introduction. So whether you use LSTM based decoder, or even a transformer based decoder architecture, modern day large language model utilizes transformer based architecture only. Okay. So moving onwards, you'll be you'll be utilizing this, whether whatever the application you build, text to text, or speech to text, text to speech. There are numerous applications you can develop, right? Once you have encoder-decoder architecture. Even in our foundation course using LSTM, we have discussed so many ideas, right? One is a chatbot idea we have discussed, chatbot. But whatever in our lab exercise we have dealt is the language translation, which is called as a machine translation. English to French we have done. And can we use this idea? In fact, one of the assignment tasks related to this is I have given a chatbot task, question answer. You particular any domain, you can create a question answer, and you can, instead of your English as the input sequence and the French as the output sequence. So your question should be the input sequence, and the answer to that question should be the output sequence. You can create a chatbot. What are all the other applications I can extend for this using encoder decoder architecture? Like can we do text summarization? In fact, the lab notebook I have shared with you, which is the lab 10 after this. Okay, so we'll be doing this lab 10 only in the next session on Wednesday, but all the necessary inputs related to the transformer model, theoretical understanding concept, we'll be doing it. Maybe a brief introduction about this lab 10, just by loading the transformer architecture, that part alone, the first half of this lab 10 alone, we'll discuss. Probably the second half we'll continue in the session 11. So we have two use cases related to large language model, lab number 10 and lab number 11. So what I was talking about, you have to understand this processing as this exercise treatment. You can take it forward even for encoder decoder modeling also. Don't confine your idea strictly to Siamese. It's all depend upon how I take the results forward. Okay, how we take the results forward. So let me try to show that diagrammatically. Okay, what we are going to do in this exercise, but what you can do it in general whenever you deal with the speech data set. So speech data set is a time series data, so I can represent that as x of t mathematically, which is nothing but a digital samples. It is considered as one-dimensional array. Assume it's like a row vector. In our examples, can you see the wave 1? What is the length of the samples? 1,84,320. 1,84,320 samples. So the number of sample size is based on the sampling frequency. Okay, at what sampling frequency, at what is the duration of the signal we record. Usually for the speech signal, it's 8 kilohertz. If it is any music signal and all, we use stereo recording and all, right? Musical sounds and all, slightly higher frequency, because you know that music range, it have 20 hertz. It is audible range like 20 hertz to 20 kilohertz. Okay, as a thumb rule, your sampling frequency should be minimum 2 times of the maximum frequency content. Even if I put the upper limit 20k, what is the minimum requirement to deal with any audio which is required is a 40 kilohertz and above. Okay, so for stereo we use, I think, 44 kilohertz music sounds and all. So according to your sampling frequency and the duration of the signal, say for example, if I'm recording, capital T specifies the duration. If I do the 5-second recording, 5 into 8, 40,000 samples we get. As the sampling frequency increases, obviously the number of samples also increases. So we know that it is highly redundant, right? So this is the time series in time domain. It is in the time domain. Here we are going to see the pattern matching. Okay, one is pattern matching. We are discussing this lab 9 exercise to the context of the pattern matching. But however, you can take this idea even for the language modeling, for the pre-processing your speech data set. So what we are going to do, this x of t, we are trying to convert it to frequency representation. Okay, with the help of coding, I will explain shortly. So these are, we call it as a frequency representation, Fourier coefficients, particularly short-term Fourier transforms. So most of the popular Fourier transforms has fixed points, coefficients. Say for example, if I take 1024.50 or STFT, so the entire samples is represented with few number of Fourier coefficients. What does this represent and all? I'm going to explain. Okay, first I'm giving you the overall context. And you can apply convolution 1D, okay, to further represent these frequency domain representation with more condensed form of feature. More condensed form of feature. You may ask, sir, why don't we directly apply convolution 1D over here? Convolution 1D. Can I apply convolution 1D? Can I prepare this time domain as the feature of this time domain? Can I use it for the language modeling? Strictly prohibited. If you try to do it, it will be like a highly noisy data you will be encoding. Not like a text data, because your text tokens are very refined. But whereas your time domain, time series data sets are having a lot of redundancy, we don't apply convolution 1D. Maybe you can apply convolution 1D for what kind of application? If you have a different application, this is acceptable. As a quick interview question, can anyone tell me for what kind of application you can take your time domain representation directly? You can take convolution 1D. If you do, if I do, what kind of application? Simply, if I do a classification task, isn't it? If I wanted to go with encoder only design, you remember encoder only design, which comes under using encoder only design, we can classify a sequence data. Even our sentiment analysis of the text sequence also comes under encoder only design, isn't it? So whenever you do an encoder only design, if at all, if I wanted to classify, discriminate a two time series, okay, you can very well directly represent your convolution 1D, and then you can do it. No. For forecasting, you should not use this. See, the forecasting will work with the original features, original time representation. Okay, original samples. We don't extract features. So for forecasting problem is different from classification problem. Suppose I'm dealing with 33 degree Celsius, 34 degrees Celsius. Assume that Chennai daily temperature 34.5, 36.7, 38.6. If you are doing with the forecasting problem, we have one of the Google stock price case study we have done in our foundation model. Refer to that for the forecasting. So we have dealt something like what is the sequence length we are going to consider for the forecasting problem. This is decided based on the autocorrelation score. After looking at the lag, okay, how many lags I'm going to consider. And accordingly, we have prepared X and Y, isn't it? So based on every 3 day, past 3 days, we defined these three or input sequence, and this is the output. Next, 34, 34.5, 36.7 represents the input, and 38.6 is the output. So for forecasting problem, we work with the original representation of the numbers. If it is a temperature, we'll work with the number temperature. If it is like a stock value, we'll work with the stock value. If it is rainfall data, we'll work with the rainfall data in millimeters. If it is a sales value, we'll work with the original sales. So we never apply, don't ever apply convolution for forecasting problem. Okay. At only one place we apply convolution for the discriminating. I wanted to classify a two time series based on, okay, this is one time series, say it is like a hot weather, okay, and this is during the winter, okay, your winter you have a different range. I can build a model as a discriminator model. I just feed this time series and this time series. My model will say that, okay, these time series is recorded during summer season. This time series is being recorded during the winter season. I just classify two time series. Whenever you wanted to classify, discriminate two time series, you can very well go ahead with convolution only. But for forecasting, we don't apply convolution. Directly, I work with the original values. Okay. So this is about forecasting problem and the discrimination problem. What we are talking here is about sequence modeling. That means whenever you are going to use the speech data or music data or audio or data for encoder decoder kind of design, those cases, okay, we have to convert that into frequency spectrum. In the frequency spectrum, here of course you are allowed to apply convolution, and then you can take that input sequence for your sequence modeling. Okay, or you can directly, there are different people's they use a different, again it is a design strategy. Sometimes people uses only directly, they take the raw frequency representation of the speech. Okay, a few applications they develop using taking the features of these, and they can go with the sequence model. And here it is a pattern matching. Okay, here it is a pattern matching. So once again, let me summarize. X of t is a time domain waveform. For forecasting problem, no convolution only, no Fourier transform. Okay, directly you work with the raw representation. Case 1. Case 2. In case 2, you wanted to work with the sequence, numerical sequence. Once again, it is a numerical time sequence. discrimination. Discrimination means as a classifier or classifier. Here, okay, you can take convolution only. You can also perform a classification by converting this to the frequency domain. That is also, let me write it here. You convert this to x of omega, okay, as a frequency component. To differentiate this, let me plot the frequency, discrete frequency component like this manner. And you can take it for classifier directly. Okay, directly you can train a classifier. Or when you directly work with the raw time series, you can use convolution 1D and then you can take it to the classifier. Okay, because the raw data is like highly redundant. Okay, one way is to reduce the redundancy is apply convolution and then you can take the convolved result as a feature. You can design a classifier. You know how to design a classifier, just as a dense layer. Or another way to reduce redundancy is take the frequency spectrum, use the frequency coefficient and then build the classifier. Sometimes people still they wanted to have a more condensed form of the features. Okay, so there are two choices, right? Taking the frequency spectrum, either you can directly design a classifier, okay, or apply convolution 1D again and then design a classifier. Okay, you have two choices. This is for discriminator or classifier. So number 3, case number 3, it's for the pattern matching, right? That is what this notebook is going to deal with. So two pattern you are comparing. Okay, anchor to the positive, anchor to the negative. For pattern matching, what is recommended is convert this to x of omega, x of omega. Okay, calculate the distance. Like the way how we calculate the distance for the feature map for the images, this x of w and x of w, it's going to be like a feature map for the time series. Okay, what kind of feature map? It is a Mel-Frequency Coefficient. This Mel-Frequency Coefficient, another name is short time Fourier transform. Mel-Frequency Cepstral Coefficient. There is one more extension of this. MEL, Cepstral, CEPTRAL, Cepstral Coefficient. So what is the difference between these two guys? Okay, you are going to understand by the end of this session. So this is here I have not applied convolution 1D. Please make a note of it. Here there is no need of applying convolution 1D. Number 4. This is for encoder decoder design. Okay, encoder decoders here, like sequence to sequence model, sequence to sequence modeling. Whenever you take speech data for sequence to sequence modeling, you once again we start with x of t, which is a time domain. Okay, a time domain. Convert this to x of w. X of w. Okay, and then you can encode this sequence. Encode the sequence. Again, two variations like in classifier, how you have the two variations. Either you can directly take the coefficients and directly take it to the encoder, or what is another choices? Alternative is you can apply convolution 1D and then you take it to the encoder. Two options are there. At the end of the day, we have to experiment and see that for our data set which works very well, we can take it forward. So all four treatment I have summarized. Okay, you have to follow whichever the application you build accordingly. You have to make your choice. Any question on this? Is it clear? So now we'll move on. Okay, so now we are going to understand certain technicalities okay, related to whatever the packages I have used in the notebook. Okay, to comprehend just 10 minutes. Okay, 10 to 12 minutes. I'm going to discuss about the idea behind what is Fourier transform, and why we go for short-term Fourier transform, and this STFT is called as this. Theoretically we call this STFT, but in application people use this as a Mel frequency. Mel means windowed frequency. Okay, and another term we use in this notebook is MFCC, Mel-Frequency. Okay, the extension of this. Additionally, CC stands for Cepstral Coefficients. Okay, there is a close resemblance between these two guys. Okay, what is the differences? So initially, to start with, what is a Fourier transform? Then you'll go to STFT, and what is the difference between this MF and MFCCs? Once we understand theoretically these ideas, then understanding the code is very simple and straightforward. Generally, in any time domain, okay, in any time domain, suppose I have a sinusoidal waveform like sine. Generally, how do we define a sine waveform? Sine omega t, isn't it? What does that omega represents? Angular frequency. Mathematically, how do we define angular frequency? 2 pi f. Okay, so I'm not going to the details of this hardcore signal processing. What is the necessary level signal understanding? That alone I'm going to give you. Okay, so 2 pi ft. Suppose I wanted to draw a sinusoidal waveform for 50 hertz. Okay, any software you can generate an equation like this: 2 pi 50 t. Your t axis is defined as a discrete axis like 0 to say my upper limit is like 10 seconds. Okay, discrete. This interval is inverse of your sampling frequency. So what is the duration of one discrete sample to another time sample is depend upon a small t suffix s is inverse of your sampling frequency. Suppose my sampling frequency is 1 kilohertz. Okay, if my signal is being discretized, okay, digitized at the rate of 1000 samples per second, that is the meaning of 1 kilohertz, 1000 samples per second. Inverse of it, it is going to give the duration. What is the difference between one sample to the another sample? So if 1 kilohertz is my sampling frequency, okay, what is the interval between two discrete samples? Your TS is just inverse of this, 1 divided by 1 into 10 power 3. What is this? 10 power minus 3. How can I call this? 1 millisecond, right? So the difference between one sample to another sample is 1 millisecond. So you can, in any software, not only in Python like MATLAB or R software, you can define the range for t starting 0th second goes up to 10 seconds. What is the interval? Interval is 1 by fs, or directly you can specify 0.001. Okay, 0.01, and then you can define this equation sine np. I don't I don't remember NumPy having the sine function, but basic math library in Python having the sine function. You can write straight away. You can write this equation, and then you can do a plot. So you can see the sine waveform. Whenever you try to plot a sine waveform with one single frequency, you can see a beautiful waveform like this. Okay. So in signal processing term, this is we called as a one period. whatever the basics you are learning for this 10 to 15 minutes could be useful for your sequence to sequence modeling also. Okay, don't think this is specific only for this lab notebook 9. So this is the generalized fundamentals I'm teaching. Okay, this is one positive cycle, one negative cycle comprises the time period of this waveform. How we define the time period of this waveform? Time period is defined as 1 by f. At what frequency we are generating? 50 hertz, right? 1 by 50 hertz. So which is equivalent to 0.02, right? So this duration is 0.02 seconds. Again, this duration is 0.02 seconds. See, from this time axis, if I just simply measure, okay, from this point to this point, what is the duration? If I see my time axis says 0.02 second. Easily I can compute my frequency. What is my frequency? 1 divided by 0.02, which is nothing but 50 hertz. But practical signal does not have one single frequency component. That is a challenge, isn't it? Like speech data or any sensor data, vibration sensor or musical notes. It is like a combination of so many frequencies. Even with the same MATLAB exercise or Python exercise, you just try to add one more sine waveform, maybe with 100 hertz. Even with one extra frequency, if you add, it's very difficult for you to comprehend that waveform. You know how that waveform looks like? Okay, that waveform may be looking like, it won't be like a smooth waveform like this. It is nothing but it is a combination of 50 hertz and 100 hertz. Just like earlier, only one frequency component. It is very difficult for you to here. Of course, you can see this somehow. You can see the shape of the waveform. You can track the shape. Okay, you can track the shape. It looks like a sine waveform. But measuring this duration again, taking the inverse, you cannot find out what is the frequency because it is a mix of two frequencies. You have mixed two frequencies, additive. You have taken two frequency additively. So whatever we see, this is the time domain. In time domain, okay, for practical data set, okay, like a speech data set, this is a speech data set. This is the time domain. In time domain, y-axis is the amplitude, right? What we call your time resolution is 100% and the frequency resolution is 0%. What is the meaning of it? For practical data, you don't get any information about the frequency in the time domain. That is the meaning. Got it? Similarly, okay, when you convert this and try to see the spectrum means a Fourier transform, Fourier spectrum. You will have x-axis is a frequency axis. Okay, assume okay, this is some voice data set. Our spectrum maybe looks like this. Frequency spectrum. Usually the full range of the frequency spectrum goes up to 0 to sampling frequency range. Okay, if my sampling frequency range is 8 kilohertz, it is okay to see one half of the spectrum because a Fourier has a symmetry property. We used to see half of the spectrum. Another half of the spectrum will look symmetrically like a mirror image. So what is the meaning of this? Why there are certain portions are tall, the heights are high, tall guys, and moving forward the shorter one. What is the meaning? The magnitude of the Fourier coefficients is very high. This is just for an example and just telling. My low frequency is dominating here. That is the meaning. My low frequency content is dominating here. Comparatively, these heights are very shorter heights. My high frequency content is very less. That is the meaning. Just for simplicity, like the previous example I told you, just a two additive component of 50 hertz. Okay, 50 hertz and 100 hertz components. How do you create this waveform? Like a sine 2 pi Okay, 50t plus sine 2 pi 100t, and you make it some variable like this, and the plot in the t-axis you are plotting as t need to be discretized like this 0.001 colon 10 seconds. So for 10 seconds duration, it is going to plot this. Okay, so this is the typical representation. Of course, you adapt it according to whatever the software you use it. Whenever you apply a spectrum, because it has only two frequency components, isn't it? Your frequency domain, you could notice there is a peak at 50, okay, another peak at 100. So this is called Fourier spectrum. At 50 hertz, you have some magnitude. This height represents the Fourier coefficients. The other coefficients are very short, almost very close to zero, which indicates there are two frequency components in the signal. This is the frequency domain, right? In frequency domain, my frequency resolution is 100%, but my time resolution is 0%, isn't it? What is meant by time resolution? Okay. For this kind of this is what we call this deterministic signal, but a practical signal which is non-stationary in nature. What is the meaning of non-stationary? Because it is just a synthetic data, right? Which is a mathematical data. So throughout my time axis, my statistical parameters are fixed. That is the stationary. But practical data like speech data or any sensor data, musical time series and all, non-stationary in the sense, your statistical component are not same across the time axis. See, if I take the sinusoidal pattern, when you look at the sinusoidal pattern, whatever the statistical measurement, if I calculate for one portion, will be the same as the another portion also. Say, for example, my mean value is 0, right, with respect to the 0 reference, and the standard deviation. Say, for example, mean and standard deviation, any portion, whichever the portions I measure, it will be the same. That characteristic of the time series is called stationary time series. But in practice, most of the practical time series are non-stationary in the sense. One simple example of non-stationary, let me with the deterministic equation also, you can create a non-stationary. Now I'm going to define up to 0.5 seconds. I generate a waveform for 50 hertz component. Okay. Another 0.5 seconds, I generate a slightly higher frequency component, 100 hertz. Because this example you can easily connect rather than I give a speech data and all, it has too many frequency components, right? At one portions you will get a different frequency component. Sometimes you pause at the time you don't have any frequency. Again, your pitch will vary at a particular, your loudness vary. So at different time instances, your frequency keep changing it. So I just give a very deterministic example like this. Okay, this is up to 0.5 second, and the second half is high frequency. Okay, this is a low frequency, and this is a high frequency. And if I apply Fourier transform to this a non-stationary signal, why we call it non-stationary? Because my statistical component is not same here, isn't it? Look at my standard deviation of this portion is different from the standard deviation of this portion. So my statistical quantity changes because this portion is a high frequency compared to this. Whereas like a stationary component, after mixing two waveforms like this is how waveform it will look like. So at every band, okay, the same 50 hertz component as well as the 100 hertz component is available throughout the signal. But that is not the case in this non-stationary, because my 50 hertz component happened at the first half of the period and the 100 hertz component happened at the second half of the period. So when we apply a traditional Fourier transform, what is the limitation here is, of course, my Fourier transform is going to give me the spectral component. Fourier component says that, hey, there is a 50 hertz, there is a 100 hertz. Fine. But if I ask my Fourier transform, can you tell me whether 50 hertz happened first or 100 hertz happened first? Fourier transform does not have an answer, because in Fourier transform, we know that time resolution is 0%. So what we are trying to do is, we are trying to do a windowed Fourier transform. That is called short-term Fourier transform. Windowed Fourier transform. So before I go to the windowed Fourier transform, okay, why we are going for the windowed Fourier transform? To understand the context better, let me reverse this. Okay, for the first 0.5 duration, let me have a high frequency component. Up to this 0.5 second, now I maintain 100 hertz. The second half, I am maintaining 50 hertz. This is another waveform. Okay, say this is x1, this is x2. Now I take x1 Fourier transform, I display this. For x2, I take a Fourier transform, I display this. Fourier transform, there is no change for x1 and x2. It looks same because it has a time resolution 0. This x2 100 hertz happen first, but for x1 50 hertz happen first. So when I use a windowed Fourier transform, I can get the time resolution as well as the frequency resolution. So what does your short-term Fourier transform is going to deal with? You are going to apply the fixed window. Okay, say for example, I choose a fixed window in terms of the sample size. Okay, I choose a fixed sample size, and for this fixed window, I see the spectrum. What are all the frequency component, the earlier part of my waveform, and then I analyze what are all the frequency component in the later part of the waveform. Since I apply the fixed windowed Fourier transform, we know that, okay, in the first portion, whether I got 50 hertz happened first. Since I am applying the windowed Fourier transform, I know it very well because I only apply the window. I know it very well. I'm asking, hey, what is the tonal component in the first portion, this window? I'm asking Fourier transform. It is going to say 100 hertz. Here, when I ask, it is going to say 50 hertz because I am only operating the window. So I know the position also. So I got the position. Position means what? The time resolution. Time resolution along with the frequency information. That is why we go with the STFT. Whereas, okay, the variation of this STFT is called as MFCC. What does this MFCC is going to do? It's an interesting task. It is something related to the wavelets, but of course we are not going to go through the hardcore wavelet concept. Just an idea of the wavelet, it's adapted. What this guy is going to do is, instead of using the fixed window, it is using a variable window size. Let me erase all these things. And another interesting aspect is, the window size is automatically selected based on the frequency component in the signal. See, in practically in the speech signal, not every portion of the speech need to be analyzed with same level of sensitivity. Because how our auditory system responds, our human ear, responds to the sound. Our human ear requires more samples to resolve in the high frequency, and it required less samples in the low frequencies. That means what? Say for example, this portion, let me consider as a low frequency. Okay, and let us consider that this portion is a relatively higher frequency. In the high frequency side, okay, each and every tiny portions need to be resolved very sharply. That means I'm going to use, okay, very narrow window to resolve these portions. because the high frequency, so I use a very narrow window. Relatively, whenever I come with the low frequency, I no need to analyze very closely, right? Because it is a low frequency. Even if you try to have a larger window to cover this, your human eye can resolve this. So this is called dynamic window size. MFCC uses a dynamic window size. First, it will apply across the whole samples with variable window size. It is going to plot the waveform with the different scales. Initially, it apply a narrow window across the whole signals. It is going to show the spectrum and different scale. The scale slightly broader window. It's applied over the whole. So it's up to you, right? Whenever you wanted to analyze the low frequency component, you go for the broader scale. Assume this is a narrow scale, little. So with a different sized window, whichever the scale you wanted to analyze the pattern, you can analyze. So it is a windowed Fourier transform. So whenever you go with the windowed Fourier transform, you can achieve both the time resolution as well as the frequency resolution. But what is the bonus? What is the bonus in MFCC? You are analyzing the signal with a different scale. In STFT, you just in simple STFT, you have got only this range. That's all. Only this band alone you will get. But here you will get a multi-band. Why multi-band? Because you have applied a different size of the windows. So we can specify the band, number of bands and all. We can, in our built-in function, we can specify how many scale you wanted to apply and all those things, or you can go with the default also. So we are going to analyze both the features. Okay, one is a single band, simple STFT. Simple STFT is called as a Mel-Frequency. Okay, and multi-band is called as a MFCC. So let us understand these coefficients for the pattern matching, both Mel-Frequency as well as MFCC. Whenever you come across these questions in the interview, people ask you about MFCC or Mel-Frequency. You can easily relate this to the context of, don't try to explain the literal definition based on the book definition or the Wikipedia definition. That is not encouraged. Okay. Try to associate this in the practical context, try to explain. Mel-Frequency is nothing but your short-term Fourier transform. Okay, windowed Fourier transform. And whereas MFCC, first you tell what MFCC stands for. MFCC stands for Mel-Frequency Cepstral Coefficient, which is related to the Mel-Frequency. Whereas in Mel-Frequency, it is a single fixed window. The frequency bands are analyzed. Whereas in MFCC, with a different size of the window, the spectral components have been analyzed. So it's like a multi-channel. This is like a single channel. So first I'm going to analyze for the first waveform. Okay, first waveform is my anchor waveform. So we have loaded, and to extract the samples, you know the procedure. .ys is a method to extract the samples, just like your time series. I'm plotting this waveform. So, and also first anchor to positive. Okay, let me read my positive. Wave2.oes. First, let us compare the time domain plot. Okay. The same sentence, we are learning deep learning. Okay, look at this. This is anchor. This is positive. Physically, structurally, it looks slightly different. Okay. At the same time, I wanted to see the negative. Wave number 3 for the negative. Look at this, the wave number 3, this is negative. So it's very difficult. By the plotting, we cannot make any sense. So we try to see the spectral band, Fourier spectrum. Okay, simple Fourier spectrum. So 3 stages we are going to move on, right? One is a simple Fourier spectrum. Number 2, STFT. Number 3, MFCC. Now record 1, I wanted to show the spectrum. So we have a method called make spectrum. You can plot the spectrum. Here your f-axis is frequency axis. You can see the upper limit is 22.5 hertz. That is my sampling frequency here. This package, this waveform uses sampling frequency. At what sampling frequency the system has acquired my speech signal is not 8 kilohertz. It is 45 kilohertz. And whatever the plot we are seeing is half of this, 22.5 kilohertz. So this limit, if you measure, it's found to be 22.5 kilohertz. The right extreme is 25K. Okay. But what you understand, because it's a male speaker, right? Male speaker, as I told you, the majority of the spectral components you can dominated over here. And slightly make a note of it. Okay, this high, of course, we don't go beyond 15 and 10 and all. Let us focus our attention up to this portion, maybe around 7K or 8K. This portion, this is for the male, right? This portion, if you look at for the female speaker, okay, this magnitude and all slightly higher. Again, visually, it's very difficult to comprehend. Only if you extract these values and if you square sum and take an average, definitely that magnitude will be large for female compared to the male. If you are doing a simple discrimination task, even with the Fourier coefficients, I just I give a cutoff value. I take all the value above 4K or 4.5K till 8K. Assume like a 4K to 8K, these band samples alone I extract. Okay, I can simply compare it. Easily I can differentiate which is a male speaker or female speaker. Now let us see the spectral band for the female speaker. Okay, let us see for the female speaker, wave number 4. Can you see the magnitude of the high frequency tonal component, particularly this portion and these portions? If I zoom it, you can able to see there are some small elevations over here. If I zoom it, you can carefully see. Whereas for the male speaker, this is almost something like completely flat. And again, somewhere around 2.5 to 4 kilohertz, the magnitude is slightly larger for the female when compared to the male. This portion you could see, this portion is relatively smaller compared to this. You have to look at the height. Look at the height. So maybe if I take the cutoff from 3K to 8K cutoff, definitely the magnitude of the coefficient component for the female is very high. So this is negative, right? If you are very curious about positive, another positive, let me check for positive, anchor to the positive. This spectrum also looks almost same as your earlier spectrum, not a very big change. Can you see this is something like a flat? There is no component, right? Can you see there is no frequency component beyond 5K? It's completely flat. But whereas in the female, you have seen some slight traces of frequencies even in the higher range. But cumulatively, if you look at the percentage, This will dominate, of course, 90%. The remaining few traces beyond the 5 kilohertz up to 10 kilohertz, hardly 5 to 10%. Whereas for the male speaker, this portion dominates around 95 to 98%. This portion contribute only 1% to 2%. That is a major difference between the male and the female frequency components. So, okay, one at a time we'll investigate. So first for the investigation, we'll take an anchor with a positive. Okay, anchor with a positive. So in my W1 is my anchor, and wave 2, I have the positive. Okay. So both cases we have investigated the frequency spectrum. So to explore more for short-term Fourier transform and MFCC, okay, the basic package won't support. So again, we need to go for some third-party package like Librosa. It's a popular package to work out these features, STFT and MFCC features. Currently, I have my anchor. Let me make a comment for your reference. Okay, this is anchor. It's stored in W1 SAMP. And W2 SAMP is nothing but positive. It's stored in W2 SAMP. So using Librosa package, we are applying STFT, short-term Fourier transform. And this logarithmic scale, I apply only for plotting purpose. Please make a note of it. The people working with the Fourier transform, short-term Fourier transform for the first time, they get puzzled with this log function. Why do we apply the log function? Because the magnitude range of the coefficients are a bit skewed. So you are familiar with the logarithmic scale in the graph sheets and all, right? So when you apply the logarithmic scale, you can the skewed portions you can very well distribute in the values. Then only it is visually pleasing. Those coefficients you can able to discriminate it. Otherwise, in the original range, it's very difficult to differentiate and understand. So this I'm applying the logarithmic scale for the resultant Fourier coefficients, and then we are plotting the waveform. Look at what are all the value we are passing in the spectrogram on the Mel scale. So frequency scale, STFT scale. This is the sampling frequency. I told you it's a 44,100 hertz. I told you approximately 45 hertz, isn't it? So it's a approximately 45 hertz. Precisely, it is 44,100 hertz. That means Fs by 2 is 22,050 hertz. That is 22.05 hertz. So your logarithmic scaled value along with your sampling frequency you have to pass. The beauty of STFT is it provides both the time resolution as well as the frequency resolution, isn't it? Your time axis as well as in the y axis your frequency range also you can see. So which portion of the time you have got different frequency components, you can analyze time axis as well as the frequency axis. First, let us investigate the anchor male. In the below, I plot the positive, anchor to the positive. First, we'll do the visual interpretation. Okay, first we'll try to see the visual interpretation and then we'll try to do a quantitative interpretation. So visually, it's very difficult to make any difference. Again, this is anchor and this is positive. Moreover, it looks same, isn't it? Can you see? We have a this portion, a dark blue patch up to this, and again here you have noticed towards the end of the waveform. Okay, towards the end of the waveform, you have got this patch. And again, you have some slight discrete patches over here. Only this much you can see. The dark blue, comparatively, it is a lower intensity decibels, and the lighter one with the higher decibels. So that is the color variations they have provided. So how to interpret? At the initial portion of the waveform, okay, at the initial portion of the waveform, your frequency, what is the combination of the frequency components you have got? As you move on, as you move towards this side, what are all the frequency components? So relatively, these portions are dark. Okay, the magnitudes are smaller. Relatively, these portions are little brighter. The magnitudes are larger. The larger magnitude. This is the smaller magnitude. So that is the one you can interpret in terms of the loudness in decibel. Another interpretation is in terms of the magnitude of the coefficients. So before we compare these values numerically, okay, let us try to plot the negative. For negative, you can see a very nice difference. Instead of record 2, I go with the record 4. Record 4 is a negative, right? Let me load my negative samples. W2. W2. Let me directly come here. So I update. Better we'll keep 2 variable. Okay. So this is for 2. So we'll W2 will reserve for positive. Let us not overwrite that. And let me keep W3. This is for the negative. So W3 sample. W3 sample. So one more cell. This is negative. This is W3 sample. So that I can easily compare. Okay, W1 is undisturbed, right? Anchor. This time let me show you anchor to the negative W3 SAM bypass. Librosa STFT, we are passing W3 SAM. This one, this is for the negative. Visually, we could notice some variation in these patterns. However, how to compare this numerically? Just you copy paste this. Okay, let me keep this separately. Every time I no need to rewrite this. W2 SAM, and this is W3 SAM, W3 S3. Now we have got S1, S2, S3. Okay, I told you the logarithmic version, log of S3, I should use it only for the plotting purpose. But for the calculation purpose, okay, I should use the raw version. So before applying the log. Now we are going to calculate distance between anchor to positive. Another cell we are going to calculate anchor to negative. Let me call this is a D underscore AP. Okay. It is going to perform the vectorized operation S1 minus S2 squared difference. Let me show you how it is working on the vectorized operation. If you want to understand this alone, let me run and show you. Okay, the length of these samples are different. That is 1024 point STFT applied to so this representation is 1024 cross 361. This representation is but usually when we work with multiple data, because we didn't standardize the data alone, okay, we have to shape all the samples to the uniform size, because you look at the original samples when we acquired. Length of W1 underscore SAM 1,84,320. So this is a bit longer duration signal. Two lakh 21,760. Okay, the first one is a bit shorter. Okay, let us crop. Okay, the silence portion and all we'll remove. I would like to take it from 80,000 sample onwards. 80,000 colon. We'll keep 1,75,000. 1,75,000. Length of W1. Okay, we'll truncate to this 95,000 sample. Let me plot this W1 underscore SAM after cropping without silence portion. Okay, we have the only whichever the portion we have spoke only this portion. So this would be more refined representation. So all three samples we have to make it to this uniform length 95,000 or even 90,000, and then if we compare, that would be like a more meaningful comparison. However, for the display purpose, let me plot the raw sample so that we understand which portions we have cropped it. Okay. In the same manner, I'm going to crop the second waveform. $75,000 to 75. 80,000 to 1,75,000. Length of W2 underscore SAM. Okay, this also. So neat and clean portion alone. Finally, for the wave 3 also 80,000 colon 1,75,000. Let me plot W3 SAM. Slightly increase my sample size because the third, the female speaker, some portion of their tonal quantity is truncating. So if I start with 78,000, Now all are 97,000 samples. Okay, this is better. 1 lakh. We'll make it 1 lakh. 75. So all three waveforms are now 1 lakh. Okay, we make it as standardized. 1 lakh sample, 1 lakh sample, 1 lakh sample. Once again, apply this. S2. So it is going to perform vectorized operation. Squared difference sum. So how to understand this 196 is 196 fixed bands which is run across the entire 1 lakh samples. Entire 1 lakh samples, 196 fixed bands have been applied. So in every band, we have got 1024 FFT coefficients, including the zero starting value. It shows 1025. To be precisely, if you wanted to band wise calculation also, we can do like, because I have calculated the total distances, total including all the bands, I cumulatively calculated the distance. But if you wanted to do it for the first band alone, 1025, 1. Okay. So in that case, you have to extract the first band. How do you extract the first band? Because this is the shape, right? Suppose in case if you wanted to extract the first band, the initial portion of the waveform, 1024 points. How you have to extract S1 square bracket comma 0. So let me show you the length of this. It is just a one-dimensional array. Now it is like a matrix format, isn't it? So for every band, you have got 1024 coefficients. So this alone. So this is the first band. Again, the second band. Second band, it applied. It's a fixed window. Likewise, 1 lakh sample, it is covering with 196. So that means 1 lakh divided by 196, you can easily calculate per window how many samples it covered, isn't it? So per window, how many samples it covered if you wanted to calculate? 3, 4, 5, 1 lakh divided by 196. 510 samples, roughly, because it will round off whichever the window which is not sufficient, equal it's not maintaining, it automatically pad with zeros. So roughly 510 samples per window, it computed 1024 points coefficients. So band-wise, analysis will go depth, unless otherwise if you wanted to build some serious application, definitely we can spend a lot of time on it. Just we are going to understand the conceptual. For the conceptual point of view, let me do it for one single calculation across all the bands. I just computed the distance. Similarly, this is the distance between anchor to the positive, isn't it? Anchor to the positive. Now I just copy paste this. S1 to S3. Can you see the huge difference? Anchor to the negative, the distance is large. So again, here also we can use the threshold, like the way in the Siamese face recognition, we have used the distance cutoff. Hope you remember, like 0.7, 0.8, like that. Here, for Mel's frequency, you can choose a particular cutoff, and MFCC also you can choose a different cutoff. Up to the distance of 2000 or something, you can say it's a positive. For quick understanding, now you can change another positive also, because I have two positives. Little bit I modulated my voice and I spoke. If that modulated voice also this distance comes less than 2000 values, then you can say the maximum deviation can be within 2000. I can understand is the same person voice. If any value goes beyond 2000, I can understand that is a different person. So this is to quantify in terms of the Mel frequency. So let me copy paste this line below this. Okay, this is the distance between anchor to the negative, and this is the distance to the anchor to the positive. So always we should get a smaller distance to the positive and the larger distance to the negative. So this magnitude. If you selectively do the calculation of certain bands, still you can refine the results. But however, I have cumulatively taken all the bands. Okay. But this itself, it's more than enough for the